Hi everyone, my name is Zhang, and I'm currently a PhD student at the University of Southern California. Today, I will present our work, SanRazor, reducing redundant sanitizer checks in C and C++ programs. This work was done when I was an intern at ETH Zurich before. As we know, C and C++ programs are unsafe, and they suffer from varieties of vulnerabilities like buffer overflow, user after free, and undefined behavior. To detect these software bugs and vulnerabilities, various sanitizers have been designed, such as AddressSanitizer and UndefinedBehaviorSanitizer. However, in practice, the runtime overhead caused by sanitizers is very high, which inhibits their adoption in production. For example, our results on SPEC benchmarks show that the zero mean runtime overhead induced by AddressSanitizer and UndefinedBehaviorSanitizer can be up to 74 and 160% respectively. So the problem is, can we reduce it? Prior works for sanitizer check reduction fall into two categories. They either use sanitizer-specific static analysis to remove only semantically redundant sanitizer checks, or they use cost-based heuristics to remove only costly sanitizer checks. In this work, we explore a new novel design point. It introduces a general framework, SanRazor, for effectively removing likely redundant checks by performing check redundancy analysis. At a high level, SanRazor is designed as a hybrid approach. First, it gathers coverage statistics of checks during a profiling phase based on a program's test suite and their dynamic patterns. It then extracts the static data dependencies of checks as their static patterns. Finally, it analyzes the similarity between these dynamic and static patterns to pinpoint and remove checks identified as likely redundant. Specifically, SanRazor starts by identifying both user-defined and sanitizer checks. In LLVM-IR, each check can be represented as a comparison instruction, followed by a control flow transfer instruction. It then instruments each check to record code coverage patterns of each check. Next, it selects a suitable workload and runs the instrumented program with this workload to gather code coverage for each check. Specifically, we count how many times the control flow statements, namely the BR statement, are executed. We also record how many times the true and false branches are taken by checking the 1-bit operand of the control flow statement, namely the return value of the ICMP statement. We refer to them as the true branch covered times and the false branch covered times of a check. The dynamic pattern of a check is defined as a tuple consisting of its total covered times, true branch covered times, and the false branch covered times. After capturing the dynamic pattern of each check, we then capture their static patterns. Specifically, we trace the data flow information from operands of each ICMP statement. Specifically, we use a deep first search and derive such a tree structure to represent the data flow dependency. After this step, we design 3 schemes by calibrating the extracted static features. For L0 scheme, we gather all the leaf nodes on this dependency tree into a set. For L1 scheme, we canonicalize the collected set of leaf nodes by eliminating all constants from the set, except constants operands from the comparison statement. For L2 schemes, we canonicalize the collected set of leaf nodes by eliminating all constants from the set. The static pattern of each check is defined as the canonicalized set of leaf nodes, namely their value dependency sets. After getting both the dynamic and the static patterns of each check, we perform check redundancy analysis. We first compare the dynamic patterns of each pair of checks. If they share identical coverage patterns, we think of them with same dynamic patterns. We then compare their static patterns. If they share identical value dependency sets, we view them as redundant checks. If 2 checks have both the same dynamic and static patterns, we consider them as a pair of likely redundant checks. Note that we don't remove user checks. Instead, we only prune sanitizer checks in case they are redundant with respect to either user or other sanitizer checks. After that, we set the condition of the redundant check's control flow statement as false, such that the branch of alerting will never be executed, and the redundant code will be removed by that code elimination in LLVM. In summary, SanRazor is a general framework for effectively removing likely redundant sanitizer checks, and we integrate it into LLVM framework by providing a wrap of clan, namely SanRazor clan. To demonstrate the effectiveness of SanRazor, we first give the cost evaluation of SanRazor. We use SPEC CPU 2006 benchmarks to perform cost study of SanRazor. As shown in these figures, SanRazor can reduce the geomean runtime overhead of an AddressSanitizer from 74% to the range between 28% and 62%. Also, it can reduce the runtime overhead of UndefinedBehaviorSanitizer from 160% to the range between 37% and 124%, depending on which schemes we use. Notably, for L2 scheme, it achieves a geomean runtime overhead of only 28% for AddressSanitizer and 37% runtime overhead for UndefinedBehaviorSanitizer. We also report the number of removed sanitizer checks and the saved CPU cycles by reducing the sanitizer checks. As shown in this table, SanRazor eliminates up to 30% address sanitizer checks, which saves 41% CPU cycles. It can also eliminate up to 39% undefined behavior sanitizer checks and saves 77% CPU cycles. Next, we present the vulnerability detectability study of SanRazor. In total, we select 38 CVEs from 10 commonly used programs. Our results show that SanRazor can detect at least 33 out of these 38 CVEs. We also compare SanRazor with ASAP, which is a tool reducing sanitizer checks based on their cost. Note that ASAP allows us to configure arbitrary overhead budget. As shown in our results, within the same budget level, namely the cost level of sanitizers, SanRazor has significantly better vulnerability detection results compared with ASAP. This is mainly because removing high-cost sanitizer checks neglects the important observation of sanitizer redundancy. Finally, we discuss the application scenario of SanRazor. The focus and the typical application scenario of SanRazor are to practically accelerating sanitization-enabled programs in production usage. When a production software can't afford all the sanitizer checks, SanRazor can help effectively remove those checks that are least useful in terms of discovering unique problems, as shown in our evaluation results. Moreover, SanRazor may be combined with complementary approaches to further reduce the overhead of sanitizer checks. Since it's generally orthogonal to other sanitizer tools. For example, by combining SanRazor with ASAP, it's possible to run those sanitizers in production at only 7% overhead. Well, we can still get the security benefits and vulnerability detectability of these sanitizers. In summary, in this work, we present SanRazor, a novel and a practical tool for sanitizer check reduction. SanRazor is designed as a hybrid approach to remove likely redundant checks. Our evaluation results show that SanRazor can effectively lower the overhead caused by sanitizers, while still retaining high vulnerability detection capability. Thanks for listening to this presentation. If you have any more questions, feel free to reach us via email. We also release our artifacts for SanRazor on GitHub.